My name is Morten Linderud. I go by the nickname of Foxbaron on the internet. I have been doing open source software development for around 10 years now. I've been an Arch Linux developer since 2016, where I've been doing packaging, been part of the security team, Reproducible Builds, and maintaining different projects. I care a lot about usable security tooling, so I've been doing sort of projects around Secure Boot, UAPI, and now lately a bunch of TPM projects. I'm also a board member of Hackeria, who's heavily present today, helping to run the hardware hacking village. When I don't do a lot of open source stuff, I work at DevOps at NRK, working on things like the elections and sort of the visual storytelling stuff. But first, let's go back to the basics. So we should make an SSH key. So when we do SSH, we preferably would make a key. We'll call this ed24519. Do we want a passphrase? Yes. Let's use 1, 2, 3, 4. 1, 2, 3, 4. And now we have made this SSH key, and we want to use this to authenticate. So what we do is that we copy this to our server, which is very important, because you can tell because it says important in the domain. And then we type in the root password. And next time we try to connect to this SSH service, we can do, we type in the password, and we get access to our service. So the cool thing about this is that we now have access to a root key with a SSH key instead of using the password. And the reason why we can't, why the user can't see the key is because ed24519 is because of the permission of the key, or I accidentally leaked the entire key. So if you now try to access the server, my key is exposed. This is what we usually call key compromises or key extractions. The service now, you can now copy the key, get access to the service, and it's not connected to the service. It's not, you can connect to this SSH service, and we prefer to have better ways of preventing these things. So this is not limited to SSH keys. This can also be done to things like cookies, access tokens, and things that are not directly connected to your hardware or your identity, but can be abused without you having access to the key. It can be used for privilege escalation, impersonation, or you can do things like compromising GitHub repositories if you just have access to the key. SSH keys are trivially brute forceable if you know the password, and that's sort of the thing you want to prevent. This isn't really a theoretical thing. You have a fairly recent case now where an APT, I think, that got access to a vulnerable Jenkins server. They extracted SSH key from Jenkins and then used that to compromise the GitHub repositories of the organization, which is bad. We should try and prevent that. It should be more strongly tied to something that would prevent you from taking the key away. You also have GitHub that leaked their RSA host key by accident, which would allow you to do some form of SSH man-in-the-middle attacks or intercept the connection. So what we would preferably have is some way to have device-bound keys. This would prevent people from taking our keys and use them without having access to our machines. We'd like to strongly tie this to some identity claims, like your Microsoft identity at work, or your Okta accounts, or some other provider. And we'd also like to try and make sure that SSH keys are strongly tied to the machine you're using them on. That would help you prevent things like, it would ensure that you also have access to the correct device, and for an enterprise setting, you would have to also be from a device that is enrolled MDM or some device that your company has control over. And all of these sort of things together would prevent you from, would actually like allow you to sort of have more trust in SSH keys or other credentials that you would like to secure. So one of the cool things that is sort of ubiquitous these days is Trusted Platform Module, or TPM. You can use YubiKeys to sort of secure them better. But TPMs are very much sort of standard hardware on most machines today. They are sort of secure crypto processors. They do things like check the boot integrity and do platform attestation. That will take a little bit look on. They're usually implemented as some form of separate hardware, some sort of module that you connect to your motherboard, or they can also be sort of implemented as part of your CPU firmware. I think Intel used SGX, but now it's in some other thing, and the AMD Secure Enclave thing. It supports platform integrity, which allows you to have some reassurances in how you boot and which state your computer is in. They have a way to do keys and hierarchies, which we'll take a look at. And then attestation, which is strongly tied to the machine identity part that we'll look at afterwards. So the way the platform integrity thing works is that you have these platform configuration registers. There are 24 of them, and they are some part of the boot chain, which is hashed and stored as part of the TPM. These do a lot of things. 1 to 7 is usually the platform registers, a part of a boot chain, and the rest of them is sort of the application or the runtime part of it. For the Linux part of this, there's the UAPI group specification that sort of details which register is used to what, and you can use this to create either policies or lock keys towards the TPM. We also have the concept of hierarchies and seeds. So TPMs are sort of not great computers. What they do is that they have hard-coded seeds and other seeds that you can create keys out of through a key derivative function. And you have 3 seeds by default. An endorsement seed is the ones that sort of burned into the TPM, and this is for the lifetime of the device. The owner's hierarchy or owner seed is for the lifetime of the owner that has it. That can be rotated. And then you have the null seed, which is basically for the lifetime of you boot the machine. The seed gets seeded, and you can sort of do a temporary credentials under that seed. The endorsement seed is chained back to the manufacturer, which means that you can get a certificate, and you can verify that it's an authentic TPM because it was signed by the manufacturer. And you can also do shielded keys, like create some key, extract it out of the TPM, and it will be secure. So the way this works, because it has a terrible API, is that you say which hierarchy you want. So this is the endorsement hierarchy, which produces a context. We can make a key out of that, which in this case is an RSA key. We have then the public part, which is the public cryptography part of it, like the public exponents and stuff. And then we have the private part, which is a sealed blob to the TPM. What that allows us to do is to take the load this public and the private part, which can be carried outside of the TPM, back into the TPM again. In this case, gives a new context. We can use that to create some form of data, which we can then sign with some message and use to verify signature. So TPMs also support policies. That means that you can sort of explain to the TPM what system state you have to use it on, or what user or admin can be able to do some operations with the key, which will allow you to sort of only have these keys usable if your system is in a given state. They also support sign policies, so you can rotate them and stuff, but that's a little bit beside what we're going to do today. The main problems with TPMs these days, though, is that they're sort of slow. They're not HSMs or hardware security modules. They are fairly slow. Most sort of discrete TPMs do like 7 or 8 signatures a second, which is sort of usable, not super usable for anything that requires a lot of activity. It still has limited cryptography, so most of them these days only have RSA 2048 and then the NIST P256 and 384 curves. And it only really supports the SHA-256 and the SHA-384 hashing algorithms. That means these things are not super secure for like quantum cryptography and stuff. And I think they're starting to be a bit on the low end of the bit size with the new new bit demands that NIST is looking at. Also, the things that we need to do is that we need to have some more user-friendly tooling. That's sort of the commands I already showed you. Terrible. I don't remember that offhand, and neither should you. And the other issue, though, is that it's not really supported by OpenSSH, because OpenSSH doesn't really like TPMs that much. But there are still other ways of using it with SSH, and that's the SSH agent. The SSH agent is some daemon that allows us to hold private keys for SSH. It communicates over a Unix socket, and it helps you to do things like caching the password or caching the PIN. You can also use it to offload key operations. So the cool thing with SSH is that if you do an SSH agent, you create some key to the agent, and then you list it. So it means that the agent is aware of the key. What we usually do when we do SSH is that we refer to a private key. But when we have the agent, we only need to refer to the public part of the key. That can either be done as part of the SSH configuration or part of the SSH command line instead. And what that allows us to do is to effectively implement some agent that does the TPM key operations for us and only use the public part to identify the key. Implementing an SSH agent is fairly trivial, at least in Go. It implements sort of a full SSH agent client interface along with an SSH server, and makes it easy for us to sort of interact with SSH as a whole. So that's what I did. I wrote an ssh-tpm agent, which allows us to do TPM keys. It supports the key creation of most of the algorithms that ssh-tpm does. It also supports some of the OpenSSH key formats, and it uses the Google Go TPM libraries to do the TPM interactions themselves. So the way this works is that we have some authentication socket. We have the SSH agent. We can then make some TPM key, which uses the same interface-ish as the OpenSSH stuff. We can then create or add the new TPM key to the agent. And the standard SSH tooling is going to be aware of the key. We can also make a normal SSH key as long as it's one of the supported algorithms. And then we can also import it into the ssh-tpm agent, so we can sort of rewrap the existing key into the TPM. So this is cool. It also has some other support keys, some other supported features like some proxy support and some host key support, which allows you to sort of combine multiple agents into one front end, or have your SSH host keys as part of the TPM. But the main question, though, is it secure? So I've already leaked my key once. So let's do it again. So what I'm going to do now is I'm going to create a new key in the TPM. The pin is 1234, 1234, and now we have the key. What I'm going to do now is I'm going to go on my GitHub. We're going to go and add this key to my account. Ooh, that's the wrong thing. We're going to call this BSides Oslo. We're going to look at the public part of this key. We're going to take that, add it to our GitHub. And to prove it works, so now we have added the key to the agent. And we're going to prove it works by authenticating with github.com. That should work. And we have authenticated to GitHub. If you're interested in the key, that's the key. So if you try and take a print screen of this or try using it, you won't be able to. And if you want a QR code for it, what's it? Cat-id is .tpm. Here encode. OK, I forgot the command line for it because I didn't prepare it. But here's another SSH key that I've uploaded to my GitHub as well with the password 1234, and that's the QR code of the pin. So you can try hack me or my GitHub if you really feel like it. And this sort of solves the SSH key problem we already have. I've given you my key. You're probably not going to be able to use it, which is a huge improvement over what we already have been doing. The way this works is through a spec called the TPM 2.9 key file spec, or that's how we serialize the keys. It's an AS1 format for storing the TPM keys, and it also has several providers. So OpenSSL has a TPM2 provider, and the Linux kernel also supports these keys as well. And that allows us to use some sort of common format for all of these TPM keys, which allows us to or make keys somewhere else, insert them into our agent, and so on. It supports loadable, importable, and sealed keys. And because there was no good framework for this in Go, I wrote one myself, which is located here. And it allows us to sort of easily create TPM keys. So if you use Go and you want the TPM key, we can just define a new loadable key. We can give it a description. We can say it's an elliptic curve key with some 256 bytes of security. We can write out the bytes of this key into a file. And if we want to sign things, we can just use the standard crypto signer API in Go. And it just works, which is quite nice. You can also make keys yourself through the Go TPM API. So the template is how the TPM knows what objects it should create. We can create a loaded object, which is how the TPM loads objects. And then we can sort of serialize our own key with a description and the public and private part of the key. And we can write this out onto a new key file. And this is sort of this is nice. This solves the key problem, but it needs some way to distribute this key. Remember, we're making a CA. We want to have some way of distributing these keys. And SSH has this certificate, SSH sort of the certificate key types. And they allow us to do ties, have some central authority that can sign SSH certificates that we can use instead. It can be tied to some user. It can be tied to some capabilities of SSH, like if you want a real terminal or not. And you can also do a cool thing, which is giving a time age to the keys. So you can say it's only valid for 5 days, 1 week, or just 5 minutes if you really want to do that. And what this allows us to do is not only have keys that are non-extractable, but it will also help us have keys that are short-lived, which helps sort of lessen the compromises of it. So another Go example, we define some time range right now and then add 5 minutes to it. We can make a new SSH key, and then we can do SSH certificate. So we say it's the user search. We give it a key ID, which is the TPM. Which says valid after, valid before, which is sort of the time range it should be valid. And we can give it a set of permissions. That's sort of the standard ones. You can do agent forwarding, you can do port forwarding, you can get the real terminal, and then you can also load the RC file of the user. This is signed, and then the user can use this to authenticate with the server. And the way that SSH trusts the CA is through this trusted user CA key, SSHD directive. Yes. So now we have sort of solved the, So now we have device-bound keys, and we have some way of distributing them through a ca-authority. Now we want to have identity claims. Identity claims are something that we trust. It can either be sort of your Microsoft Microsoft's authentication portal. It can be signed by Microsoft, and then you can go validate that these attributes to your login is actually from Microsoft itself. This is usually implemented through something called OpenID Connect, and it's sort of standardized across multiple vendors and allows us to sort of do these things. An identity provider is called an IDP, and they sort of are signed from the provider itself. OpenID Connect is based on something called JWT, or JSON Web Tokens. They can be validated remotely, which means that we can have a token, trade it around, get the public keys from our provider, and then sort of check that they have been signed itself. The way these things work is that we have an algorithm that says how it's signed. This part is protected by a signature, which has several claims from our identity provider. In this case, we have the email, and we have that the email has been verified. And then this entire thing is protected by an RSA signature. So the identity providers themselves, there's a bunch of them. You have Okta, which you can use, Keycloaks for self-hosting, Microsoft Entra, I think, that a lot of people probably use in their day-to-day work. And then you also have Google through their sort of their portal. And all of these things that are usable for users, you can sort of make people log in, and you can get back some different claims. Personally, I'm interested in GitHub, but GitHub doesn't actually have an OpenID Connect towards users, so you can't use them. So I had to sort of try and work around that. And to sort of figure out how these providers are configured, we have this sort of endpoint, .well-known OpenID configuration, which lists a bunch of sort of the setup for OpenID Connect. So this is the one from Microsoft Online. And you see that they support a bunch of different claims. Most of these are connected to their Azure stuff, I think, but they still have sort of a bunch of sort of different claims you can authenticate and verify they actually work. The one thing we are interested in, though, is maybe the ACR value, because that's the value that tells you if you are actually using two-factor authentication or not. Because just using sort of username and passwords, that's not super useful for us. We want to have some way of actually verifying identities. We want strong identity claims. The way people usually do this these days is two-factor authentication. And we want to know from the IDP if we actually have a user that's authenticated with two-factor authentication. This is done with the ACR claim in the OpenID Connect spec. The issue, though, is that it's there, but it's not really standardized. So the values, or sort of the two-factor authentication claims from the IDP itself, we don't really know what it means. It's all vendor-specific. And the only two sort of semi-standardized values are silver and bronze, which I don't really know what that entails. But it means sort of that figuring out if somebody is actually using two-factor authentication isn't easy. Google refuses to tell you this because they don't want vendor lock-in. They would prefer that you don't know. Microsoft gives you some of these values, but I couldn't figure out what the values were. So I needed another way of sort of supporting IDP providers without having to sort of hard code a bunch of identity providers and figuring out how they work. So Sigstore is a Linux Foundation project. It's mostly used for keyless signing, which we don't really care about in this context. But what they do have is that they have a public for good federated IDP, which is hosted by Linux Foundation. It does identity providers for us, so you can do Microsoft, Google, GitHub through a single identity provider. And as long as we decide that we trust Sigstore, then this probably works for us. And this sort of, what should I say, quick hack to get this working instead of sort of hard coding all of the different providers. So the next issue, though, is how do we know that the authentication that we want is actually from the CA? So we want the certificate authority, and we want some identity claim, but we don't want any claim. We want the claim, or we want the identity, the login that the CA has requested or not. Because if we have no way of verifying it, then somebody can just man-middle some login through an IDP provider. And then they can just send it to us, and we'll just blindly trust it. So we need some way of figuring out how if this actually belongs to us. So I spent a day looking at this list of values that we can control and sort of how we can sort of use this to insert something that we can check for. And after staring at it for a bit too long, I realized that the nonce is client provided. So that's supposed to be make sure that we don't sort of reuse the authentication scheme, but that also means that we can insert whatever value we want. So I decided that the CA can make a random string, insert it into the nonce, and we can just check for it instead of doing another dance with it. So the goal then is that our CA is going to give our client some value. This value has to be present in the sign-in of the service we have, and then it's signed. And that probably gives us a claim that the identity provider has signed an authentication request from us at some point. So we now have device-bound keys. We have identity claims, or some way of at least ensuring that we have identity claims. The next step, though, is that we want to make sure that the device is the one that we are using. You want, like I said, you probably want some device that's from your enterprise or some from your organization. So you need some way to prove that this machine is from us. So machine identities. It's when people sort of work from home and stuff, we don't have a lot of control. Some people log into their internal services from their home machine because it's practical instead of carrying a work machine everywhere. But if you have a lot of access, like on SSH, you preferably would not want that. You want it from a machine that you know is good, that you control from the enterprise. So the endorsement keys from TPMs is sort of the hard-coded one for the lifetime of the machine. It can't sign things. So the TPM people decided that we need something more complicated instead, called credential protection, and we have attestation keys. In theory, this should should give us some form of anonymization, so that if you want the identity of machine, you can do that without actually disclosing which machine it is, which is a bit interesting, but we don't care about that. So we're just going to do credential protection with endorsement themselves. And the way the TPM works with this is that you have something called certify and attestation keys. So certify allows us to verify or sign that an object was created on the TPM. TPMs have some strings that will refuse to sign, and that allows us to ensure that sort of a key was created on this TPM and that the TPM has actually signed this. We have a bunch of attributes that says that the TPM key can't be exported out of the TPM itself, and then we can sign all of this. And because of the attestation key, we can chain this back to the endorsement key itself. So the way these sort of challenges work is that the credential protection proves possession of some machine resident key. It's a shared secret, it's encrypted, and we can do these downs remotely, send it to the TPM, and then TPM can unlock it. And what that proves is that TPM we send the encrypted credential to is from a key that's on the TPM itself. So credential activate is the thing that we have to run on the local on TPM. And make credential is sort of the encryption operation itself. It's not unique to TPM. We can do this remotely with just public information from the TPM. And then we can send it back. So the way you prove position is that we use make credential on the CA. We have the endorsement key, we have some attestation key, and we have something that we want to decrypt. We send this blob to the client or the agent themselves. The client is going to decrypt that blob. It's going to send this blob or the secret string or whatever we wanted to decrypt back to the CA. And that helps us to prove possession of the machine that we're actually using. So that means that we have device-bound keys, we have identity claims, and we have some way to do machine identity. Yes, so the SSH agent is going to do the TPM key operations for us. We have a way to prove possession of an identity and the machine. So this leads sort of to the thing I've been hacking on since summer, which is ssh-tpm-ca-authority. So let's see if this demo actually works. So what we're now going to do is that we're going to run the CA authority. And this is effectively the CA. It runs locally in this case because it's easy. And I'm first going to SSH into my NAS server at home. This should fail. It doesn't fail. OK. We're going to try SSH, and now we get the password prompt to the client up there, just so it's easy to see. And what I'm going to do now is I'm going to run the authority. Yes, that one's gone away. And then I'm going to SSH into my NAS. This NAS is then going to open the SigStore identity provider. I'm going to click login on GitHub. And then we authenticated. It's going to issue a short-lived certificate, and it's going to SSH into my server. And if you look at the output of the SSH agent, we see that this has provisioned an elliptic curve DSA key and the certificate as well. Yes. So what this is effectively is that the certificates, these provisions, are short-lived. They last for 5 minutes, and then we need another one. We have done some way of identity authentication through an OpenID Connect provider. And behind the scenes, we've also done the machine identity parts of it, which is the credential protections. The also cool part about this is that we haven't actually re-implemented either the server or the client. We're just hooking into the agent and then using that instead. Other solutions, like the teleport client-server stuff, involves that you have to sort of do full buy-in of the SSH server and the client, which is probably a hard sell on a lot of enterprises, or you yourself if you want to use this. And this sort of is just a cool little hack. So the way this works is that we make a key, which is supposed to be the CA key. We set up a configuration, which says which SSH host that we want. We give it a CH file that is supposed to sign the request we want. And then we just give it a list of users that have access to this server. So in this case, this is my user. I've decided that I wanted to use GitHub. Email is the one that I should preferably be logging into when I use this tool. And EK is the endorsement, hard-coded endorsement key, which is part of my machine and sort of the thing I have to use to do the machine identification. Yes. So to getting the endorsement key from the machine, I didn't get to figure out a better way to do it, so I wrote my own little tool. And this is sort of the hash of the public part of the endorsement key. And that's sort of to make sure that we have it enrolled before we use this, because it's hard to sort of establish this key after the fact. So it's preferably done as part of sort of enrollment procedure. So you at some enterprise getting the endorsement key and before handing it off to the user. And that sort of is the way that to prove that the machine is ours. Running the SSH, the CA server currently just does sort of the local host thing, all standard. And the client setup is sort of the interesting part, because this is part of the SSH configuration to client. So SSH supports something called match host exec, and that means that if you match on some host, it's going to run a secondary command. In our case, we have our special ssh-tpm-add command, which just communicates with our CA, with our host and our username, and that's sort of what's fetching the certificate from the CA server into our agent before authentication starts. So the attestation protocol itself is, what should I say, not huge, but a bit complicated. So I did a blog post explaining this a few months ago when I originally wrote this talk. But I'll try and explain it here as well. Hopefully some people find it interesting. So the server has two endpoints, one called attest and one called submit. Attest is the one that we use to initialize the authentication towards the CA. We don't know what the CA has, but we have to provide our username, which host we're using, and the endorsement key. and then submit is the sort of two challenges that we need to do through our identity provider and the credential protection. So we do creation of two keys, which is the attestation key called the AK, and the TPM-bound key, which is the key on the machine that we're supposed to be using. We submit this attestation. The OpenID issue challenge is effectively the CA verifying that the identity provider has given you valid credentials. We decrypt the credential on the client, and then we submit all of this. And back again, it provides a signed SSH certificate that we throw into our agent. So the way this works is the bound key, we do the tpm-ca-create command, which gives us back the attestation keys. Certify creation is the one that we do to sort of make sure that the key itself is part of the TPM. So this is the agent communicating with the TPM. We do the same dance again for the TPM-bound key, which is the agent communicating with the TPM. We do creation, and then we certify the creation. And that's going to give us the attestation of the keys. The attestation itself is that where we give all of our SSH host, that's SSH username, and the keys that we created. The CA authority is going to do some pre-validation of all of these things, ensure that it exists in our configuration, ensure that we have these things validly signed. And we're then going to create two secret values, which is then done with the credential protection, and the nonce, which is then used by the OpenID Connect issuer, and we send this effectively back. So the client doesn't know which OpenID Connect server it uses, and it doesn't know anything in front of the request itself. This is represented as some Go structures, which is translated to JSON. So we have the attestation parameters, which is the host, the user, and the attestation information. All of this is sort of just flat JSON with some base64 encoded strings. And back we get the interesting part, which is the credential, the encrypted blob. We get the secret, which is the public part of the shared secret that we do, which is some part of some elliptic curve Diffie-Hellman challenge itself. OpenID OIDC is the issuer that we're supposed to be communicating with, and the nonce is part of the OpenID Connect challenge itself. OpenID issuer challenge, that's the agent connecting to the OpenID Connect issuer. So we do the login flow with the nonce that we set ourselves, and we get the JVT proof back, which is signed by the OpenID Connect service or provider. The agent is going to chat with the TPM and get the credential decrypted, and because we use the public part of the endorsement key and the attestation key, this can only be encrypted if we also have the private part of the endorsement key. Back is going to be the credential, which is the random string we have to send back, which proves that the machine is authentic to the CA. And when we submit this to the CA authority, we sort of send back all this information, and the CA authority is going to check that everything is valid. It's going to take the OpenID Connect JVT proof, check with the OpenID issuer if it's actually signed. It's then going to check that it has all of the correct configuration that we want, and then ensure that the decrypted credential from the client is the same as the one we try to send. It will then take the public part of TPM, synthesize SSH key, and then send this back to the agent itself, which is what allows us to sign this thing. So the challenge response here is which we send from the client to the CA before we get signed SSH certificate back, is a secret, which is the decrypted blob, and the JVT string, which is the proof from our OpenID Connect provider. And back we get the signed SSH certificate, which is the byte string that we'll throw into our agent. And the end result of all of that is that we get two keys. One is the private ECDSA key, which is part of the TPM agent, and then the certificate, which is part of the certificate that we use to validate the connection itself. So improvements, is the protocol good enough? I don't know. I am sort of an open source hacker dude. I'm not like a proper security engineer, so I have no clue if this protocol is good. But it works, and it gives us some stronger claims on our SSH keys. We should probably do some more pinning of the platform keys. We can chain the entire endorsement key back up to the manufacturer, including the serial number of your machine. I need to figure out how that works. I know Teleport does part of this as part of their enrollment procedure. And SSH is a bit lacking. So when you get like a signature request from SSH, the agent doesn't actually know which server it's signing something for. We only get this blob. Please sign this with this key, and we don't know any metadata around the server. It would be preferably better if we could have some way of like a signed statement from the host keys saying this is our metadata. Please sign this, because it will be easier for us to reason about what we are actually want to sign in context. There's also sort of an entire sort of extension thing with SSH agents, which we can only control if we actually re-implement the SSH client itself. And it would preferably be a good idea for the SSH agent either to be able to offload this to another agent or something else. So there's sort of a bunch of issues with OpenSSH as well. So yeah, I've now shown how we can sort of do TPM-bound keys with the SSH. We have written some CA-authority that is able to take machine identities and then identity claims and machine identity claims and sort of hand out short-lived SSH certificates. And we can use this as part of our authentication scheme towards our SSH servers. All of the source code is public, it's on the GitHub, and it's there if people want to take a look at it. I should probably say it's like more of a point of concept than a finished thing, but the TPM agent itself is used by multiple people in this room, I think, maybe. So that's something you can look at if you find it interesting. If you have questions, I have a blog, I have an email, I have a Mastodon account if anybody wants to look up that, and my GitHub is Foxborough as well. Thank you.
Thank you very much.